Hi, good afternoon, and welcome to day 2 of Cloud Next. I'm Nisha Johnson, a product manager at Google, and I'm joined by Ben Cuan from Reve and Raja Jadeja from Google. Before we start, I just wanted to share that we do have a discussion group on this topic at 4 o'clock, Reve AI. So if you have questions and you want to have a discussion with other attendees, it's a great place to attend. So AI is more than just compute. To actually get high tokens per compute and high utilization, you need a platform that can handle heterogeneity. Heterogeneity is when your AI demands vary across compute, space, and time. And compute utilization is not all you need. You also need day-to operations like observability and security. And in this session, we'll also cover a little bit about TPUs and how it can help improve obtainability and cost efficiency. We recommend 6 pillars to cover the Reve and GKE stack. So the first part is just starting with the right compute for the right job. Then you have to make it easy to select, ensure that your workloads work performantly at high utilization, and even when compute spans across different clusters and regions. And of course, you have to make sure that they are observable, secure, and easy to fix. But before we dive into how the stack solves the heterogeneity problem, let's hand off to Ben to talk about Reve and their AI platform.
Awesome. Hey, everyone. Reve as a company is focused on building interactive interfaces for state-of-the-art image editing and visual understanding models. And we believe that providing direct control is essential for visual content creation. So as an example of what we've been working on, I just wanted to show you a quick 30-second demo of one of our more popular features, which is annotations, which allow users to directly communicate with the model by pointing, clicking, and drawing on images rather than relying only on text-based prompting. Awesome. So that was just a little bit about what we do. And for the remainder of this talk, we're going to focus on the ML infrastructure side of things. And notably, there are 3 main characteristics that we have to consider when we're designing our infrastructure. The first is that ML workloads, especially for training, often require really high throughput and low latency communication across thousands of accelerators, which are GPUs or TPUs for the most part. And workloads are also parallelizable across multiple dimensions, so we have to consider data parallelism, tensor parallelism, pipeline parallelism, and other sorts of parallelism all at the same time, so that we can horizontally scale almost indefinitely. The second characteristic is that we have to make our infrastructure both user-friendly to our research team, as well as to millions of users who need to run inference tasks on our models. And finally, there are multiple classes of workloads that we all need to consider at the same time. So I've classified them in maybe 4 different main buckets right here. So the first being data curation tasks. So when we're labeling or classifying our initial data set, then passing over our initial data set for pre-training, which is building our foundation models from scratch. Then inference, which is serving the requests from users with the static weights that we get from pre-training. And finally, post-training techniques such as reinforcement learning with human feedback, supervised fine-tuning, and direct preference optimization, which allow us to further customize and tune our outputs for the needs of our users and our researchers. And in order to maintain those characteristics, we use 2 primary platforms that make up the core of our infrastructure stack. The first being Kubernetes, which solves the problem of orchestration. So Kubernetes allows us to organize thousands of individual machines into a single addressable cluster. And once we have the cluster, we need to figure out how we can translate machine learning workloads into something that Kubernetes can understand. And so that's what we use Reve for primarily. Ray is compatible with many platform types, such as Slurm. So we use the kubeRay operator specifically to get Kubernetes custom resources from our Ray abstractions. So going into the main problem that we're trying to solve with these platforms and with these characteristics in mind is heterogeneity. And what I mean by that is that our workloads vary across three main dimensions: compute, space, and time. So as a high-level overview, compute heterogeneity refers to workloads that need several different types of hardware all at the same time. So for example, workloads often require CPU paired with GPU or TPU simultaneously. Workloads also vary across time. So within a single training run, we often combine tasks that take less than a millisecond each with tasks that could take seconds or up to a minute in a codependent manner. And finally, accelerators are currently pretty scarce at the moment. Maybe you've heard. And so we kind of need to get what we can get. And so therefore, they're often spread across multiple cloud providers and geographic regions. So how do we actually deal with all of this variance? I'll start with the first portion of the stack, which deals with compute heterogeneity, and specifically with maybe the first problem that you run into when you're trying to train a model, which is how do you actually get the compute that you need in order to run your workload? And right now, there are three pretty popular ways. The first one being to get spot instances. And so these are the easiest and most affordable way to get compute. So you kind of just go up to a cloud provider and be like, hey, I want to just give me whatever you have at the moment, and I'll pay whatever the market price is. So this is a really great entry point into getting accelerators, but it's really hard to get reliable and co-located blocks at the scale that we need for training. So then, okay, we can build a data center and go the complete opposite direction. But of course, this comes with a lot of problems, such as, it's really difficult and expensive and time consuming. So at Rev, we use the middle ground, which is to use a reservation with Google Cloud. And with the reservation, we're allowed to lease a dedicated compute block for a larger timescale, such as a month or a year. And so this strikes the balance between availability as well as guaranteeing uptime and the fact that we have a dedicated amount of compute that we can use without our training runs getting interrupted. And usually the next step after getting the compute is to install Kubernetes and maintain it. And this is one of the things that GKE does really well for us, is it allows us to abstract away that level of things. And so we don't need to think about operation side things for Kubernetes, and we can just focus on running our workloads. And so once we have a Kubernetes cluster, the next stage is to install kubeRay. And so the way that kubeRay works is that it translates Python, which is easy to write and understand for researchers, into Kubernetes custom resources, which are easy for me and the rest of the infrastructure team to maintain. And just to illustrate this point further, Ray really helps us abstract away a lot of the major architectural differences between different types of architectures. And so the actual contents of these diagrams aren't super important. I just wanted to illustrate just how different the left, which is the Hopper architecture, or A3 Mega, A3 Ultra, looks like compared to Blackwell, which is on the right, which is the A4 platform. Specifically, the software implementation feature that allows us to leverage this is label-based scheduling. And so this is an example of what it looks like in code, where we have a Python decorator where our research team or our developers can just choose a specific accelerator type like H100, and that will be translated into the Kubernetes world. So just to summarize that, researchers can now easily select compute types without needing to muck around with the actual insides of Kubernetes YAMLs. The high-level goal that we're trying to get with all of this is to make sure that we can be as flexible as possible for future compute platforms. So right now at Rev, we're primarily on the Hopper GPU architecture with PyTorch. And In the future, we expect that to change as things get more optimized and the state-of-the-art research changes. So for example, we're looking into maybe like GP200s, the future Vera Rubin platform, as well as TPUs. And so I wanted to pass it back over to Nisha to get more into the specifics of what TPUs and just to give you an example of what that flexibility can look like.
So Google introduced TPUs in 2015 to enable massive scale and the lowest cost per token. And that's why Google DeepMind builds Gemini with TPUs and Anthropic builds Claude with TPUs. And over the years, we've released a range of different generations with Ironwood coming up last year and this year, TPU 8T and 8I. Starting from Reve 2.55, which has been released, we will have first-class TPU support in Reve. And what that means is that any scale will natively integrate and test TPUs in their releases. This is the first time an accelerator outside of GPUs has received first-class support, while most others are experimental and supported by the community. First-class support comes with prepackaged TPU Docker images and well-tested dependencies. A big question that we often get is, how easy is it to move our Reve code from GPUs to TPUs? And the answer is that it's not too hard. The same Reve APIs that work on GPUs also work on TPUs. Reve understands TPUs. Previously, before Reve had this TPU understanding, you had to write a lot of manual scripts to give Reve that understanding of how TPU devices and topology worked. Now you can use the slice placement group API in the Reve util library and simply select your topology, and Reve will automatically schedule the workers on it with an awareness of the hardware architecture. So for example, here we're selecting a 4x4 V6E slice. Reve will select the whole 16-chip slice as a whole without fragmentation. And it will also infer the number of hosts and workers based on the topology automatically. Reve is also very easy to use when you're running your jobs, which are large scale on TPUs. It'll do automatic topology-aware scheduling on physically adjacent nodes, so you don't have to go through a lot of communication hops and suffer any throughput loss. And if your job spans multiple pods, you will need multi-slice, and Reve supports that as well. A lot of the Reve community uses Reve dashboard, and now TPU metrics are also available in Reve dashboard. If you have your own custom monitoring panel, you can also export these metrics using Grafana. TPUs are powered by the JAX ecosystem, and Reve supports these frameworks natively. You have MaxText for scalable pre-training, SkyRL for post-training, and VLLM for high-throughput serving. SkyRL already supports JAX, with support for Reve and JAX coming up in a few weeks. So Reve Train is a very popular API for training, and we now have JAX trainers as well, especially if you want to do multi-slice. And highlighted are the code changes that you need compared to GPU code. So it's just one parameter change, use TPU true, and you just have to define the topology, and Reve will automatically do the placement. If you need to do multi-slice, just define the number of workers and the topology, and Reve will automatically calculate the number of slices. One common complaint when you do training on large-scale jobs is that hardware failures cause crashes. Elastic training is a very popular feature in the GPU world of Reve. And now it's also supported for TPUs. So if a slice fails or goes down, Reve can automatically recover from a checkpoint as long as the number of workers has not fallen below a minimum threshold. And you need to also set a failure limit, because it'll retry up to the failure limit to prevent infinite recovery loops. Reve Data also supports JAX, with Reve feeding globally sharded data through JAX arrays directly. It also does multi-host synchronization so that uneven batches don't cause your workers to hang. The Ray community is also super excited about PyTorch, and a few weeks back, we announced Torch TPU. Ray does support Torch TPU, and moving from GPUs to TPUs is pretty easy. So on the left, I have an example of Ray code with PyTorch on GPUs, and on the right is the same code on TPUs with the highlighted lines showing the changes. So all you have to do is change the Ray remote decorator to point to TPUs, import the Torch TPU API, and instead of a CUDA device, use a TPU device. Here's another example of an offline batch inference pipeline. Again, all you have to do is change the CUDA device to a TPU device, import the API, and here with Ray data, you have to set the number of GPUs to 0 and select TPUs. Now, Ben will share a little bit more about temporal heterogeneity.
Awesome. Hope you all enjoyed learning a little bit about our problems with compute heterogeneity and some of the solutions. So let's switch gears and talk about the next section, which is temporal heterogeneity, which is variance across time. And the crux of this problem is just that idle compute is expensive, right? We have a reservation, and that means that whether or not we're actually using our allocation for running useful workloads, we're still paying for it. So ideally, our accelerators are working 100% of the time, but this is hard for a few reasons. So for example, bottlenecks are constantly shifting from different parts of our training pipeline. So for example, like data loading to inference to encoding, there's a lot of different places that all run at different speeds, and we all need to maintain them in different ways. And also in between workloads, there's often downtime when jobs are completed or they crash. We need to take them down for debugging and improvement. And so if we have a really big training run that takes like a few thousand GPUs and now get crashed, like all of those thousands of GPUs are sitting idle. And there's also a pretty important point on performance optimization work, which is a whole other talk in itself. So I just wanted to mention it briefly. Cool. So to make that a little more concrete, I just wanted to illustrate this example where, like, let's say we have like a workload, right? And for example, like we have some encoding tasks that maybe take like on the order of a few milliseconds, and we also have some inference workloads that take a few seconds. So you can think about this like we have like a one lane road, and some race cars are trying to share that road with big semi trucks that are super slow. And so the solution is that we can open up multiple lanes and have a slow lane and a fast lane and maybe more lanes for all of our different types of workloads. The concrete implementation of that idea is what we call auxiliary workers, which is a method that we leverage independent Ray actors for. So in this diagram here, we have our main training nodes that are running our main training loop, but we also have auxiliary workers that are managed on the side that can take care of our tasks that are temporally slower or faster than the main training loop. And just to make that even more concrete, we use auxiliary workers for our online reinforcement learning platform. So we have separate worker pools that run our inference tasks, and then when we're ready to transfer the new weights from our main training loop to our workers that are running inference, then we can use Ray Object Store. We're also experimenting with alternative ways to optimize that even further with peer-to-peer communication. So the main highlight here is that now that we have auxiliary workers and we're able to package many different types of workloads into a single job, that really saves a lot of developer and researcher time, since we don't have to deal with the additional overhead of managing a bunch of different things. Another example of a problem is workload prioritization. So how do we allow jobs to run 100% of the time while ensuring that our big hero training runs get the resources that they need without being blocked by lower priority tasks? And the way we solve that is with preemptible jobs with queue. And so for our purposes at Rev, we have two main priority classes. We have preemptible jobs, which are the lower priority data classification, things like that, that it would be great if they're running, but we can also interrupt them at any time, and it's no big deal. So what we do is we have a really big, large max worker scaled preemptible job. And in this example, we're asking for 2,560 GPUs. Well, we only have 5 pods, so 40 GPUs available, and that's great because a big training run is happening. But when that big training run crashes or goes down, we can automatically recover all of that capacity and transfer it over to this preemptible job and continue running it at a larger scale. So just wanted to share that with this strategy, we're able to ensure that a workload is running on any arbitrary node and a little more than 90% of the time. Cool. And with that, I'll pass it back over to Nisha to talk about the last portion of this, which is spatial heterogeneity.
So spatial heterogeneity is when your clusters are fragmented and you have compute that spans different regions. One example of this is when you're doing inference across multiple clusters. In this situation, when you're doing production serving, you need to manage both traffic as well as rolling upgrades. So you have a developer rolling out a new model, but now there's a bottleneck because the admins have to reconfigure networking to make sure that this model is something that's accessible to end users. And this becomes even more complicated when you have multiple clusters. An inference gateway provides a fix to this because it provides one common endpoint for all the Reve services that span all your different clusters. And this is how it works. You have inference gateway, and there's a common ingress point and load balancer. It uses the HTTP route to define the rules for directing traffic to the different Reve services that are in different clusters. And there's a separation of concerns here because the developer can just manage the inference objective, capacity, deployment, while the admin focuses on how traffic is accepted and routed through the different services. And there are 2 ways that inference gateway access this load balancer. The first is through a URL path. So if a request comes in and it's for a summarizer, it would go to the specific Reve service that matches that URL path. And if it's for, let's say, a translator, it would go to a different Reve service. The second option is to use something called routing extensions. And this is called body-based routing or model-aware routing. And essentially, it looks for an OpenAI compatible endpoint. And if a user is requesting a specific model like Gemma or Cuan, the inference gateway can use the information in the JSON body of the request and route it to the appropriate model. And it could be a different Reve service in a different cluster. This is just one example of spatial heterogeneity, but Ben will share more about how Reve handles it.
Cool. So when we're dealing with compute that's fragmented across multiple different regions, we could have capacity that's split between different geographic regions and data centers, mostly because, again, resources are scarce and we're going to get what we can get, and sometimes that's going to be in a different region from our main cluster. The problem with this is that standard distributed training breaks down when we have multiple data centers and we're trying to combine them into one worker pool, because we expect within a single training run that we have extremely high throughput and low latency, which can really only be achieved with co-located machines in the same data center. So with that being said, how do we actually take advantage of compute that's spread across geographic regions? One of the developer experience side of things that we do is leveraging Reve for remote submission. And so one of the problems that we encountered was that our researchers were used to writing their code and developing their workloads in our home cluster. So in this illustration, let's say it's cluster A in the region US East 1. And so all of their files from NFS and all of their jobs and all of their development machines are in US East 1 in cluster A. But we have some free capacity in cluster B in Europe West 1 here. The thing that Reve does that's really awesome is that we can run a submitter pod in our home cluster, and this will automatically zip up all of the code and the metadata and all of the resources that we need to run the job. and upload it to our remote region and communicate that across the entire array cluster. Another solution and problem we have that's very related is topology-aware scheduling, where when we start to think about architectures like GB200, MBL72 especially, where we have 72 GPUs that are collocated in one rack with really fast interconnect within a rack, but slower interconnect in between racks, we need to make sure that the workers within the same workload are scheduled as proximally close to each other as possible. And there are a few ways that we can do this, and I've illustrated two of them here. So one is with GKE labels. You can see here that we have labels for host, rack, and cluster, and we can correlate the IDs for the host of rack and cluster to make sure that we're scheduling our workers in an optimal manner. This also can be surfaced in the queue level, where we can specify specific node labels that we want to use. So we can just pass in topology.gke.io/rack and attempt to schedule our workers within the same rack. There's also some future explorations that I wanted to mention briefly that could allow future training runs to leverage spatial heterogeneity even more. So for example, there's some distributed training algorithms like dloco that kind of bake in this assumption of heterogeneity within the actual training loop itself. Cool. So that was a very high-level overview of some of the problems and the solutions that we use to solve the heterogeneity problem and build an AI platform. And for the last section of the talk, we wanted to just mention a few things about how we can operate such a platform. So solving problems in the space of debuggability, observability, and security. One of the features that I'm excited about that was just released is the Ray history server. And historically, it's been pretty hard to debug Ray jobs and Ray clusters that have been terminated because their Kubernetes resource goes away and all their logs and events are gone. And the Ray history server solves this by providing the same interface that we have for live Ray jobs that are currently running to terminated ones. And so we can debug them in the same easy way. With that, I'll pass it over back to Nisha to get into the more specifics about how the Ray history server works and some other features that you can look forward to.
So it's very typical when you're running large jobs to run it on ephemeral clusters, temporary clusters that get shut down either at the end of the job or because they fail. But one issue with that is that you lose the logs and the metrics that were part of the job when it terminates. And if it's a job that crashed, there's no way for you to go back and debug it. And teams solve this in a couple of different ways. The first solution is to build your own custom observability solution. But this is a distraction and it requires a lot of maintenance. The other workaround is to just keep your clusters running until you're done debugging, which wastes a lot of compute resources. Ray history server solves this issue. Google and Anyscale have come together to build a solution in open source, and it's going to be community maintained. And the way it works is that KubeRay will set up the Ray history server, and the Ray pods in a live job will write the logs and metrics to a persistent storage. Then when the job is complete, the Ray dashboard would query the Ray history server, and it would essentially show all the logs and metrics as you would experience in a live job. So as Ben shared, the experience is going to be the same for a live job as with a terminated job. And in the GA release, we want to improve the experience more. We want to offer a zero-touch experience where the Ray history server and the storage are automatically provisioned, and you have custom data retention policies as well. Another observability pain point is that when Ray jobs run, all the processes are generating massive amounts of unstructured text and just dumping it into a text stream. And when you have to debug an error, you have to sort through all of this unstructured data, looking for that one line that will show you why the task failed. Structured and severity logging solves this by formatting the logs into JSON right at the source, and it makes every field searchable. And Now just imagine that a single task is failing. Instead of scanning through all of those unstructured text logs, you just run a query that looks for the task ID and the error severity that you're looking for, and the error would then pop up. And finally, in terms of security, if you have Ray clusters that are accessible to other users in your company, in your network, and you don't want users to access, let's say, sensitive data or logs that are being generated, or go rogue and run jobs on somebody else's Ray cluster, you need to have better authentication mechanisms. Currently, the solution is to have Ray tokens, but managing these separate tokens is a headache and a security risk. And now, with Ray 2.55, you can delegate authentication to Kubernetes. And you can use existing credentials like GCP IAM or OIDC, and admins can just use standard Kubernetes roles so that you don't have to handle tokens, and you can ensure better authentication between different teams. Now I'll hand off to Raja to share a little bit about the customer trends we are seeing in Ray.
Awesome. Thank you. Cool. So I have a couple slides here just talking a little bit about what we're seeing in the market right now, what are we doing as we're looking ahead. And just want to talk a little bit about you guys. We also have a discussion group, by the way, that's set up for later today too. We'll try to take some questions towards the end of this session, but if we don't get to it, want to learn more, there's going to be a discussion group at 4 o'clock in Reve. So what are we seeing right now? What's kind of driving our roadmap? What are we thinking as we're looking ahead? Well, we've seen for a while, and part of our investment in Ray is that it's been pretty popular, especially on GKE. And what we're seeing also in the market is that it's starting to see this shift in trend, just like we've seen here in terms of the gravity of use cases going towards more inference, looking ahead towards RL, looking even towards agentic too. And what's really we've seen that's kind of driven this in some respects is that, for one, Ray was kind of born in RL. And so even like about 8 or 10 of the top OSS frameworks were all built on top of Ray itself. And we're seeing this shift in where it's really great at being able to support like the heterogeneity of compute, its data handling, all of that makes it really easy to run and start looking at that on top of Ray. And we're seeing a lot of shift going in that direction. Ray's been great when it comes to data handling, and there's a huge use case for that right now. Its ability to do pipelining and doing things in parallel, as well as the fact that it does a streaming execution engine too for Ray data, makes it very fast, makes it very memory efficient too. And that continues to be a continuing use case for Ray in our customer base too. Looking ahead a little bit towards that serving and RL side of things, the familiarity that customers have with Ray, the Pythonic experience, its ability to do that heterogeneity of compute that's been spoken about so far, in all of those areas, it makes it really a good fit for a serving case as well. And we've seen that starting to trend up as well more recently, especially as customers have started to get to the maturity of their training models, of training their models and starting to serve that out. And then as we're looking ahead towards agentic, we're also seeing that it's really awesome at handling or facilitating the orchestration to do like eval loops, et cetera. And so there's a growing use case there too. So this is some of the inputs that we're seeing that's starting to drive towards what's feeding into our roadmap. And what we're largely hearing from customers is similar to things that we've talked about earlier today as well. And so the need for better observability and troubleshooting, making it easier, especially as you're starting to work across between not just the platform side, but also the developer side too, and your research teams, et cetera, that are using it. So that post-mortem analysis becomes really, really important and critical, making it a lot easier to be able to identify what's taking place, having that availability of the structure logs that like Nisha was speaking about earlier, makes it a lot easier and more important to be able to start collecting all that information, understanding what's taking place, where it came from. And so we're spending a lot of time there, obviously with Ray History Server coming GA, looking ahead, and trying to make that a little bit easier too. As we start getting into the TPUs and PyTorch support, continue to stay aligned with the PyTorch community, the releases and the versions, and making sure that it's actually supported well on Ray, something that we're partnering with Anyscale along the way too. But we're starting to hear more and more need for even better support on the TPU side of things. And what gets interesting there as well is the fact that TPUs, we're starting to advance that architecture as we're looking ahead, and that's bringing in new opportunity, but also areas that we're looking to lean in as well from the Ray side of things. And so adding support for dynamic slicing, using, Nisha mentioned a little bit about multi-slice, and so dynamic slicing, so you can actually support that and respecting that in the placement groups and how you define that. Topology-aware scheduling and making sure all of those things work really well. And then adding in some continue to drive great documentation, recipes, blueprints, et cetera, templates for how you can use Ray plus TPUs together. All of that gets really important, and starting to continue to do that qualification as we're looking ahead towards V8 as well on Ray and making sure we're ready for that too. And so those things have been pretty important for customers as they're doing that planning, especially with Next happening right now. As we're looking towards the serving side of things, we continue to hear the need for rate serve latency, improving some of that experience, enabling that low latency use cases, reinforcement learning, and making sure things are set up and ready to go on the platform level. And then continue to add the ability to have good support for compute efficiency along the way too. And so being able to add that incremental compute as they're running those jobs, not having to preempt them in some way, shape, or form, no restarts along the way. Those are things that are kind of driving the ask that we've heard from customers. And by the way, if you are there later for the discussion group, great to hear about if these resonate with you all along the way too. So how are we planning to enable all of this? First and foremost, observability and troubleshooting. The Ray History Server is coming out later this year into GA. It's available, but it's coming into GA. And at that point in time, we're looking to automate the provisioning, storage, add retention policies, some of those capabilities too. Especially start looking over that horizon of what transpired before. Is this a repeat event? How has that changed? What are the dynamics of that? And so being able to better facilitate some of those experiences too. We're also seeing that need to kind of bring that workload and accelerator awareness closer together. And so we're certainly on the TPU side, but even on the GPU side, looking to see how we can get better metrics and information and state of things, passing that up through Kubernetes, and then passing that up into the Ray side as well. And conversely too, that should help us in the GKE side at least make lifecycle management a little bit better, understand what's taking place, are the jobs truly finished, can we start certain workflows, et cetera. Nisha also mentioned a little bit about the structured logging, bringing that error and task ID correlation together. We've already been doing some of the Ray event to Kubernetes level correlation, but now you start seeing that end to end, bringing that whole picture together starts to get really important. So those are areas that we're starting to see how we can actually accomplish some of that along the way too. And then continue to add TPU metrics. We're adding TPU metrics and observability on the GKE side. We want to pass that up into the Ray side as well. Visibility is already there through the Ray console, but we want to continue enhancing that, making that more visible all the way through. On the TPU side, more formally, we're continuing to lean in that area as well. And so we're starting to look into adding further TPU support in the Ray libraries, working on with them with Anyscale very closely when it comes to serving and RL and more. And then also on the Ironwood support, looking to get into areas around dynamic slicing, that topology awareness, and make sure that whole experience works really well for customers too. On the PyTorch side of things, optimize performance for the latest PyTorch versions. And then we're also looking at ways, speaking of the dynamic slicing, how can we actually enable a single Ray job across multiple slices on TPUs? And so as we start looking on the larger form factors of Ironwood V7, as we look towards V8, how does that look across different cubes, different slices, enabling those training workflows too? And then how do we do sub-slicing for inference jobs? Adding all of that support on the TPU side, making Ray aware and being able to take advantage of that too. On the workload side of it, we really want to get towards we're continuing to move towards improve Ray head tolerance for better uptime, and also as well as adding the in-place pod resizing without restarts along the way. For an RL perspective, especially when we start talking about Ray and JAX on TPUs, that's coming soon. It's something that's really important. Anyscale is pretty close with the SkyRL folks. We're leaning in there too. We think that's going to be important for enabling those use cases. And as we start looking at serving use cases as well, adding support for Ray Online Inference and the LLM APIs for TPUs is something that we're looking at. And so as those workloads evolve and those customers start taking advantage of that, making sure that whole picture comes together. And Queue's been pretty important for customers, not just from a scheduling perspective, but as you start looking at multi-tenancy scenarios, enabling quota management, et cetera. There's been support for Ray in there, but as we're evolving all of these areas, bringing Queue in line with that as well to make sure that it works really well for improving support for preemption handling, fleet utilization, and all of those other areas too. But we're eager to kind of hear your feedback along the way and what's important for you. What are other areas that we should be looking at in this roadmap and as we're looking ahead? So bring that to us certainly at the end of this session. Come to the discussion group, tell us about it there too. We talked about it a little bit here along the way, but we do have that session at 4 o'clock today in Reve F. please come join us. We'll have a little bit of conversation. I'll try not to cold call people too much. And then there's a couple things for you. Reve has included a coupon for Reve AI, the premium support, I think, for like a month. So take a look at that, hit that QR code, and then there's great documentation as well at the short link that's on the screen too. Thanks a lot, everyone. Appreciate the time.